So we have seen TEM waves. Now we will start with TEM wave. So here you can see TEM wave is a wave for which there is no component of EOH in the direction of propagation, and the propagation constant becomes this one, omega root mu 0 epsilon 0. This mu 0 epsilon 0 are the parameters for free space. So J beta, actually this beta is omega root mu 0 epsilon 0, this beta 0, so we can call it J beta 0 1 by m, where attenuation is 0. So if it is unbound media or free space, because generally TM wave will be appearing in unbound media, and if it is mu 0 epsilon 0, it's free space, attenuation is 0, so m will come in the denominator. So in that sense, beta will be this, phase velocity is this, means how everything changes accordingly in that way. Remember, cutoff is 0, that means from DC it can start propagating, and lambda is infinite cutoff. That means what, there is no cutoff frequency. The structure can start propagating right from frequency 0, and intrinsic impedance Ex by Hy, which is for free space it is 120 ohm. So TEM wave between parallel plates are given in figure 6.4. so this is a TEM wave between parallel plates. But remember, waveguide which is bounded by on all sides, there TEM cannot exist, as we have seen before. Now velocity of propagation is what? For free space it is defined as velocity of propagation of EM wave. This V0 Vp is phase velocity. Group velocity is what? Is the velocity with which energy propagates, and phase velocity is velocity with which equipotential surface, equiphase surface propagates along the guide. And the phase velocity is always greater than free space velocity, and in free space velocity of propagation equal to phase velocity. That is condition in free space. Group velocity in waveguide is less than free velocity, but product is always constant. Group into phase is equals to c square, free space velocity square, and the velocity of propagation are related by this. As I was telling just now, free space velocity square, v0 square, it could be c square, is group into phase. Then attenuation in parallel plate waveguide, power lost per unit length divided by 2 into power which is transmitted. 2 is accounted for two-way power transmission. So that way we can calculate the power lost per unit length by power transmitted. That gives the attenuation. And for TEM wave, it is given by this relation. So an attenuation factor is R by resistance by characteristic impedance. So these are the just standard things you have to remember. Attenuation of TE wave is given by this relation. Wave impedance, this is the wave impedance at any point between parallel plates, is defined by, you can see this one ZXY, that is Ex by Hy, a wave propagating in this plane. So Ex by Hy. Similarly, propagating along this plane is Ey by Hx at any point. These wave impedances can be evaluated from field expression here in this way. And these are some of the examples you can do. You can practice these, some of the examples. Okay. Now we have done parallel plate waveguide. If you bound it on all four media, in all four sides, if you bound it, then it becomes a rectangular waveguide, which is bounded on all four sides. So that way, if we now see waves in rectangular waveguide, then feed equation rectangular hollow waveguide. Hollow means filled with air as dielectric. Then field expression can be obtained from solution of Maxwell's equation with boundary conditions. You have to solve it, and wave equation, and these are some of the assumptions. Free free space or air, because we are calling it hollow, therefore space inside waveguide is free space or air. The walls of waveguides are perfect conducting. And then direction of propagation is along Z. The dimension of narrow wall is B, so that if dimension of narrow wall is B, I draw and show here. Then suppose this is a rectangular waveguide, then this dimension is V, this one, this is B, and this dimension is A. So this we will call it A, and this will be B. And field propagation, this is the same way, minus phase constant along and into the direction of propagation. As the media inside waveguide is air, the first and second Maxwell's equations are given by like this. It is air, so we can do it this way. And then the process for analysis, that means how to solve the equation, Maxwell's equation boundary condition, the process step is same. So that same as two plates parallel waveguide, so that I am not explaining again. The same process, you solve these equations using conditions. Then again you get here wave equations. In the form of wave equations you will get Helmholtz equation, which you can solve differential equation, then these equations will come. So this process line logic is same. By same process you have to find out these equations. So see, there are transverse magnetic and transverse electric waves. A typical rectangular waveguide is shown below. So here you can see narrow wall dimension is V, broad wall is A, and transverse magnetic wave in rectangular waveguide. You see, these are some important things, like TM waves are EM waves for which there is no component of H in the direction of propagation. This we have already understood while doing parallel plate waveguide. So here I am not repeating what is the meaning of TM and EM waves, TM and TE waves. Then the wave equations given by this can be solved using method of product solution to ordinary differential equation with known solutions are obtained. So this process, equations can be done. Finally we get the solution where we have to find out A1, A2 constants are evaluated using boundary condition. Like you see, at x equals to 0, Ez will be 0. Why? Because tangential component has to go 0. Then that you put, that is, if A1 is 0, then again you can get, so like this you can keep putting boundary condition, you can evaluate the constants, and then you get the solution. Okay. This is the final equation that we get at x equals to A, means one by one you keep applying boundary conditions and you get these. So this in details you can go through, I am not telling that. Field variations of TM11 mode. One thing more, from these solutions which you have obtained, the solutions which you have got here are, remember in parallel plate there was only one variable M. Here it is M and N, because one more that has come, one more boundary condition has come on the opposite side. So the like TM11 means one half cycle variation along X and one along Y. That is the meaning. So and accordingly the field configurations look like this. That is the meaning, TM11. So see, one field variation along X. So along X one field variation, and then along Y there is one field variation. This is longitudinal component from the side view that you can see. Now hollow rectangular waveguide. Remember, TM10 will not exist, or 01 won't exist. Why? Because you can just put M and N, you put any one 0, you see all field equations will go 0. So these won't exist. So the starting mode is TM11. Even for transverse electric waves it is the same. Transverse electric and transverse magnetic. Here the line of logic is same as the previous one, so that again I am not repeating.